Okay, our last section that we're going to talk about today is all about buffers. And buffers are commonly used both in medical research and in biology labs. So a buffer is a solution with the ability to resist pH change. So solution with the ability to resist pH change when acids or bases are added. So the most common buffer solution that you may have heard of is your own blood, right? So our body does an excellent job of maintaining its pH. And the reason it does that is within our blood, within all that liquid, we've got a really good buffer system. And we can basically measure this through something called a buffer capacity. Sorry, to go on a tangent here. Oh my goodness. Okay, the last section of chapter 9 is all about buffers. So let's first define what a buffer is. Okay, a buffer is a solution with the ability to resist pH change. Even if you were to add in more base or more acid. So let's take our bodies, for example. If you actually check the pH of something like Coca-Cola, it's got a really low pH. It's quite acidic. However, when we drink it, it's not going to change the pH of our blood, right? So our blood does a phenomenally good job of moderating our pH, which is good, right? We don't want to die from drinking a Coke. And we can actually calculate the buffer capacity of various solutions. And what a buffer capacity is it basically says, all right, you can have X amount of acid or this amount of base before you start seeing a pH change. I mean, it's not an unlimited capacity, right? So this is the amount of acid or base that can be absorbed without a significant change in pH. So in a buffer system, you might get a slight change, but the whole idea with a buffer is you prevent these radical swings in pHs. All right, so the question is, well, how in the heck do these work? So let's imagine the following. So let's imagine the following pair in equilibrium. Okay, so let's imagine that we have HC2, H3O2. This is acetic acid, and in fact, if you go to that table in your book, it's listed as a weak acid. All right, so that's going to be in our equilibrium solution, right? And then the other thing that we're going to have in our equilibrium solution is going to be C2H3O2 minus, right? And if you think about this, these look close to one another, right? So this and this are clearly related, right? The only difference is the one on the right doesn't have the proton, which tells me that it's related to the weak acid, and more specifically, it's the conjugate base of our weak acid. And if we think about it, we can kind of take advantage of this unique pairing, right? Because if we have our weak acid in equilibrium, this can react with added base, right? Because it's an acid, it'll react with base. But over on the other side, this is the conjugate base of a weak acid, which means it's going to be kind of strong, which means it can react with added acids, right? Because we know that it's going to be a relatively strong base. All right, so I'll just put a note in there that it's strong. And you might be thinking too, and I remember this bugged me, well, if this is a strong base, wouldn't it just steal the proton from this acid? Well, yeah, but then we'd just be making more of our conjugate base, right? Which kind of gets back to this idea that this is going to be all present in equilibrium. It doesn't mean we necessarily have an even amount of one or the other. Okay, so now everybody's favorite part. Let's get mathy. All right, and this drives students nuts, the math part of this, but let's just hang in there, okay? So let's imagine our acid-base reaction, specifically our equilibria. Acid-base equilibria. All right, we said that if we have our acid, I'm just going to call that HA, and we've got water, this will be in equilibrium with our conjugate base, which is A minus, and then we'll have our hydronium ion, right? So this was our acid-base equilibria that we spent a fair amount of time talking about in the past few sections. Okay, so let's define the equilibrium constant just for a review. So K, we said, is going to be equal to the concentration of our conjugate base times the concentration of the hydronium ion over the concentration of our starting materials, right? We saw this in our previous video. However, in our previous video, we said that this water is essentially constant, right? When we're thinking about acid-base equilibria, the concentration of water is really not changing over time. So instead, we move it over to this side, and we change this whole equation into the Ka expression. So Ka is the same thing. Let me even make a note down here. This is equal to K times the concentration of H2O. So these are the same. And Ka is going to be equal to the concentration of A minus over H3O plus over HA. So hopefully this is review from our previous video, but Ka values are really important and they're often used in chemistry. Okay, so oftentimes we just kind of simplify H3O plus and we just say that this is the same as H plus, right? So quite often they're used in the exact same way, shape, and form. Okay, so now we've got a little bit of review under our belt, but now let's try to calculate the amount of H3O plus. So H3O plus, which is really just the same as H plus, can be found by manipulating this whole equation up above. So if we do some algebra, we can rework that equation to get that variable on one side, which leaves us on the other side with Ka times HA, which will now be on top. If you need to review your algebra, just let me know. And A minus now on the bottom, right? So this would be our new expression. You might be thinking, okay, great. Well, where are you going with this? Well, we just said that H3O plus is the same thing as H plus. So let's rewrite this one more time. So we'll say H plus is equal to Ka times HA over A minus, right? So I'm just kind of simplifying it and rewriting it. Well, what can we do with the concentration of H plus? Well, we can find the pH. So we can find pH if we know this. All right, but if you remember, pH isn't the same thing as concentration of H+. pH is equal to negative log of H+, right? All right, so how do we find pH? Well, we can say, let's take the negative log of each side. So I would go ahead and I'd say negative log of H+ equals negative log, and then I'm going to put this all in parentheses, of Ka times Ha on top over A minus on bottom. Now, if you remember way back to your math classes, there's log rules we can use here. So over here, we said that this is going to be the same as pH. But what do we do with negative log of the rest? Well, we can leave it as is. However, what's easier to do is to kind of break this apart. And so we can say negative log of Ka, we could just call pKa, right? Because P is the same thing as negative log, right? So this is the same thing as negative log. So we've got pH equals pKa, but then we need to deal with the fraction next, which could best be expressed by writing plus log of A minus over HA. So if you need to go back and remember some of your log rules for addition, or sorry, multiplication and division, feel free to check out the Mark tutors as well. They've got some good worksheets, and I know a lot of tutors that would be happy to help. All right, so now we figured out a way to find pH. Okay, well, this is called the Henderson-Hasselbalch equation. I know I don't always show how we derive this equation, but I do think it's kind of interesting to see where it comes from. I know people typically lose me at about this section, but it's all derived from basic algebra, right? Okay, the cool thing with this is that the pKa is a constant, meaning you can find in a table. All right, and then that means if you know the concentration of A minus and the concentration of HA, your starting acid, then you can find the pH of your solution. Okay. So let's take an example situation and try to use Henderson-Hasselbalch equation. And don't worry, I'll give it to you on an exam if you need it. Okay, so a solution contains 0.10 molar NaC2H3O2 and 0.10 molar HC2H3O2. What is the pH? All right, so these were the two compounds we put forward in our hypothetical example earlier, but now we've got some numbers behind them, right? So what I would do first is I would write out my Henderson-Hasselbalch equation. So pH is equal to pKa plus the log of A minus plus the log of HA. All right, so the question is, well, which one's my acid? Well, in this case, this right here is going to be my acid, And then this over here must be my conjugate base. And another way of thinking about this is we're going to call this A minus, right? Question is, well, what about the sodium? Doesn't that have a positive charge? Well, in this case, sodium's just acting as a spectator ion. Okay, so we've got kind of what we need now. I'm going to slide this down. And we can tell that A minus has a concentration of 0.10 molar. And then HA, same thing, 0.10 molar. Well, let's try to find the pKa value for this. Okay, and I'm just going to use the table from our book. And if we go ahead and we look for it, it's a little hard to see, but they've kind of formulated it differently. It's this compound right here, and it's got a pKa of 4.74. But if you check the molecular formula, same number of carbons, oxygens, and hydrogens, right? So this would be 4.74. All right, so now I've got everything I need to deal with this math problem, which is great. So I could say, well, pH is going to be equal to 4.74 plus log of 0.10 molar over 0.10 molar. The molarity is just going to cancel out, right? So we don't need to worry about units now. It's going to be unitless. And that tells me that the pH that we get out is going to be equal to 4.74. So we're able to find the pH of the solution. All right, so that's how you do these equations. I did want to put in one important note that makes life a lot easier, and that is that pH is always going to be the same as the listed pKa value if the concentration of your conjugate base is the same as the concentration of your acid. So sometimes you don't even need to do this math, assuming that these two numbers are the same. All you really need to do is look up the pKa. All right, I hope that helps. There's a bunch of practice problems in the book. And like I said, if you need help reviewing logs, either let me know or contact one of our tutors at the Mark. Good luck studying.